again. Got my new blue glasses still on. I find them very helpful. Less glare. All right, so this is, I'm prepared a great deal for this, so it's kind of on the fly again. But I think it's really important to try to develop the graphical side perspective in math. And we're going to practice that a little bit in just a second, have hopefully some fun looking at some graphs from non-symbolic perspectives and getting hopefully a feel for the graphical process. And so it's playtime. I'm going to ask some questions, maybe amorphous, a bit amorphous, lacking form. But I want you to pause the video and really give it some thought, hopefully longer than 3 or 4 seconds, the average amount of time for a high school student to say, I can't do that. You're going to go up the ladder in math, you got to develop longer and longer periods of, I'm not sure what's going on here, but let me think about it. Moments in your career. So I've got the graphs already on the board that I want you to consider. And I'll do that right now. I'll turn the camera towards one. I've got different colors. Hopefully they show up on the screen nicely. And let's see if we can get a little feel for looking at a graph and getting a sense of what you can create through different mathematical operations and see if we can develop a little skill here. So the first one is a red graph and a blue graph, and I want you to multiply the two. Okay, so let's see if we can pin the video on that. Get nice and close. Highlight that a little more. All right, so here you go. You got a red graph, you got a blue graph. What would you get if you multiplied the two? So pause the video, give it some thought. Okay, I'm going to keep talking here, so if you want to really give it some thought, that would be great. And then it's a little disingenuous how I put this on the board because you can't really start to nail some things unless you know what one unit is in a graph. I don't think it matters so much for this one, but as we move forward, it's probably important to generate a place on the x-axis that gives you the number 1 so that you can then begin to get a feel for what's going on. But I think we can do it without that in this particular instance. All right, so what does it mean, first off, to multiply a couple of graphs? And how do you do it? Well, here we go. I hit a few things. Critical numbers. You know, where might the critical numbers be? Things that you can say, oh, I know what's happening here, even without the number 1 on the x-axis. I mean, one could be over here, for God's sakes. One could be over here. So, you know, even without that right now, I think we probably can look at some critical moments in these graphs and say, oh, I know what we're getting here. All right. And numbers, when you talk about numbers, you really got to identify inputs as being positive or negative, and then outputs as being positive or negative. Despite the fact that we work so much symbolically, those statements represent numbers. Numbers have size, right? Numbers have characteristics that we say. A number is either, the first thing you want to know about a number is it negative? Is it 0? Is it positive? Okay, can't forget that. And then as we go through this exercise, I'm hoping we develop a sense of rates of change. Okay, and then we'll elaborate on that on our 3rd and 4th examples. Okay, not so much for the first 2. Okay, and then at the very end of the video, going to actually write composite, and composite is an effigy of x calculation, and see if you can have a feel for it without going to that calculator. Can you get a sense of what that graph looks like by honing our skills here? And let's have at it. All right, so I asked you to multiply red times blue, and what are the critical numbers? Well, I think the critical numbers are when red and blue are 0. Right? Red 0 or blue 0, then our multiplication is going to be 0. So I can put some big dots right there. Our graph goes through those 2 locations. Then the question is, this looks like a critical situation, red and blue. Red and blue look very critical here. Yes, they're the same value. And more importantly, they're both positive. And a positive times a positive is going to be a positive. Question is, what kind of size would we have? Well, there we might need to know what's a value of 1 from a vertical standpoint. I mean, what we're really doing is let's write it here. We're saying y equals f of x. I'm going to stop the color coding here. And let's make that 1y. And a second y equals g of x. So what I'm really doing is I'm multiplying g of x times f of x. Okay. Can we make that a simpler statement? Yeah. I'm multiplying y1 times y2. And what are y values? They're vertical. And we get hung up on this, but it's really throwing it into a calculation and then working with that we want to develop the skill to be able to see that. So let's just say that this is 1 unit of measurement here. Let's just say that's the number 1. All right, then what do we have here? We have something like 1 times 1, right? It looks a little bit like 1 times 1. So, maybe we're right there. Same kind of distance. Question is, where do we max out? Because if we're going up to that and coming down, we got to max out somewhere. And, I'm guessing it's might even be in between the two. So we get a little feeling for that. Very quickly, too. 0 times anything, 0. 0 times anything, 0. A positive times a positive. Everywhere else, we're getting what? Everywhere else, we're getting, well, that's a negative amount. That's a positive amount. What's a positive times a negative? Sure looks like it's going down. It's going to be a negative result. And as we move to the right, that's a bigger positive. That's a bigger negative. So our product is going to continually get bigger and bigger and bigger negatively. Boom. Same thing's happening on the other side. We got negative amounts. We got huge positive amounts. And so what's the y-intercept? Well, we actually have to know that negative amount, which looks about -1. Some positive amount up here. Maybe -20, something like that. Right? That's just getting a feel for what's going on. Now, I could go symbolically. Now, I don't want to. I want to try to continue to activate that part of the brain that's just visual. Okay, so let's have at it again. And you pause the video. So we did multiplication. There you go. Have a go at division. Right? And you're going to pause the video so I don't just have to stand here for 5 or 10 minutes. Just take a couple of minutes and say, okay, what if I were to divide blue by red? So red is going to go into blue. And what kind of graph are we going to get out of that? Okay, so once again, what are you considering? Pausing the video, right? Okay, now I'll keep talking. What are you going to consider? Well, the critical moments. Critical moments. Where are the critical moments? Well, I can see 3 right off the bat. 1 right there, 1 right there, and 1 right there. All right, so let's take this one. And let's just say that that's 1 unit again, something in this vicinity. Okay, so what's happening here? Well, same number times the same number. The question is the division going to be positive or negative? You should ask yourself that question. Well, it's going to be positive. I mean, both graphs are negative, and they're negative divided by negative is positive. And it looks like they're pretty much what they are. They intersect. They're the same value. When you divide a number by itself, you're going to get 1, right? In this case, positive 1 because they're both negative. So, if that's 1 unit, then this graph goes through right there. Then we have blue being 0 and red being a negative. So we might as well go this way. Blue is 0, red is negative. 0 divided by a number? Well, that's 0. So we got an x-intercept right here. We're going to come back and work symbolically at the end of this whole process. We'll come back and look at each graph and say, what might we have been looking at and learn something from it, hopefully. Okay, but not now, not now. I'm just going to stick with visual. Red is 0. 0. You can't divide by 0. So the computer, if you're doing this on a computer, probably would go, Well, let's find out before we do that. If this is undefined, let's go to the moment just before it's undefined. And how would you describe that red? Remember, don't know if you can see this. Yes, Y's. We're looking at the Y values here. X numbers are just like the ticking of a clock. They're independent. It's what's going on at those moments. At this moment, red graph is extremely small negatively. A really, really tiny number. Then the question is, how many times will a really, really tiny, 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 tiny number, negative number, fit into, something that's about 1 unit large? Yeah, things that are really, really small can fit into large areas quite a lot. So it looks like we're going to get a very, 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 very negative number. And the closer we get to zero, woo, the more it's going to. And how about over here on that side, right there, on the other side of that dot? What would you say that Y value is? This one right there. If you said a very, very, very small positive number, you would be right. And how many times does a very, very, very small positive number fit into something that's much, much bigger? Lots and lots of positive times. So that's going to be woo right there and going up. Yep. And if you said, wait a minute, that looks like asymptotic behavior, you would be definitely right. Now the question is, what's happening as we move to the right? We move to the right. Do we see a pattern? Let me get a red marker here. Do we see a red pattern? Do we see a red pattern? Wow, I could do that forever, huh? And I guess I would be dividing that red amount, Y amount, into this blue. They'd be right on top of each other, right at that instant, but can't draw them. Well, I guess I could. This one time I'll draw it on right on top of each other, right? Red, blue. Well, what do you think? It's well, let's do it over here. It might be easier to do it over here. Red, blue. Maybe it'd be easier over here. Red, blue. Nah, I think it's better here. Red, blue. Oh, by golly gee. That into that. That into that. That into, I think we have a name for that in math. Something looks proportional. Looks like this red goes into that blue about the same amount every time. Doesn't matter how far to the right I go. Thank you, L'Hopital, for our rise over run. There's something to think about in the future. Run. Never mind. That's another topic. So what do you think? Is it okay if I say 2 to 1? Because I think it's between 2 to 1 and 3 to 1. I guess I could say 2.5 to 1. I guess I could say, how about we say 5 halves? Yeah, 5 halves is between 3 and between 2. Yeah, let's call it 5 halves. All right, so we got 5 halves. So let's see, I'm doing dots. Okay, so that's 1, 2, so right about here. 5 halves, And it seems like it's doing that forever. And if you said, oh, that looks like asymptotic behavior, I think you'd be right. Yeah. And probably the same, negative into, I think one of my lines was a little askew. So same thing, 5 halves. Trust me, it is. Absolutely. I took out the ruler and measured it. No visual, same thing. But negative into negative is positive as well, yes? No, positive here. But what happens over here? We ended up with a what? Sign change. Right? And when did it happen? Right here. When blue went from negative to positive, we got a sign change. Yeah. And then positive into positive? Yes, positive. All right, so there's your graph from a kind of a visual perspective. All right, so now we're going to try to do a little adding and subtracting. We'll keep it simple at first, hopefully. 3 graphs. You're going to add them up. Let's see if you can see that okay. Yeah, we're in good shape. So we're going to add these 3 graphs up. You're going to pause the video, give some thought to it. you're going to add red, blue, and yellow, orange, excuse me. Red, blue, and orange. Okay, and I'll keep talking, but you stop the video. Now, what are you seeing? Well, I think the critical number is right here at 0. All right. Red is 0, blue is 0, orange has got some size to it. So what if you added those 3 things? I hope you'd say it'd be right here, right? You got a 0 and a 0 and then something. Well, that's where you're at. You're at the something. Now, the really interesting thing is it going down or up from there? And why? So pause the video again. If you hadn't thought of that the first time through, now it's time to think about that. Is it going up or down? As we move to the right, we're being discriminatory here. As we move in the positive direction, we read graphs from left to right. So we'll read to the right. Maybe we'll even read to the left after we consider reading to the right. So I'll read to the right. Well, orange hasn't changed. Red, changing a little bit. Blue's changing a whole lot more. So who's winning out here? Who's winning out here? I hope you said blue. So it looks to me like, let's talk rates of change. At 0, how is red changing? It's not changing at all. How is the orange graph changing? It's not changing at all. So if change is going to happen, and change does happen, right now it's coming from the blue. So not only do we know where we are, but we know we're changing at a same rate. I'll just do that. We're changing at the same rate as this. That didn't go down as much. All right. Add an instant. There, that's pretty parallel. Pretty parallel, yeah. Good old mean value theorem for derivatives. Sorry, other topic. Going down at the same rate. I wonder how long it's going to go down at that rate. Well, orange certainly doesn't affect it. That's not changing. Once we establish where we were, I think we can ignore the orange graph. Pretty much ignore it. Oh, looks to me like red is starting to change a lot faster than blue here at some point. Looks like it's pulling up much faster rate than this is pulling down. So somewhere along the line, these things are going to counteract each other. The question is where? Where are they going to counteract each other? I don't know. So I'm going to get rid of the x-axis and just say they're going to counterattack you. They're going to counter each other. You know, where this one's going up at the same rate that's going down. Yeah, I'm going to say it's right in here somewhere. Right in there somewhere. And eventually, well, you know, there's symmetry, right? There's some symmetry here. So it looks like we're going to be going up over here, the same rate we were going down over. Yeah, I think I'm going to get a graph that looks like that. Now, where this happens, not sure, unless I start giving you a value of 1 again somewhere. Okay, but we're going to come back and we're going to take a potential, well, what would we be looking at? What would we be looking at? Okay, now we're going to do the same thing with another graph, just 2 graphs working together. And then we're going to give you a challenge question. And then we're going to go back and look at all the graphs we just created and put in some symbols for, hey, this is what we might have been looking at from a symbolic standpoint. Okay, here you go. You got 2 graphs. Let's see, you can see that fine. Oh, I'll get over on this side. Got a desk here. Might as well sit on it, get off the leg. So you got a red graph, which is not graphed well. A blue graph. What would you get if you added those 2 together? And we'll just assume that, you know, this is 1 unit somewhere in here. Right. What would you get if you put those 2 things together? Well, I suppose that we'd have some kind of doubling up on that y, right? So it would be higher, be twice this height, right? Because you're adding it up twice. It would be twice that height right here. Okay, and then this is where I think you almost have to really talk about rates of change. What's the rate of change of the red? Doesn't look like it's changing much. It looks like it's pretty constant here. What's the change of the blue? Just like the last, that's a constant rate of change, right? This one has a constant rate of no change. This has a constant rate of negative change. So if you add those two things together, looks like blue's winning out for a while anyway, but eventually, especially in this vicinity right here, I'm going straight up, right? So eventually we're going to get a bend. So this is definitely going to change right there. It should be blue, I guess. It's going to take on the characteristics of the blue. But again, we're going to get, I forgot to look at the left side of that last graph. We'll do it here. So this is a positive. Eventually, the negative's going to win out. Eventually, the negative's going to win out, and we're going to be coming down, which implies that there is a bend here. It implies that this is some point in time going to come back in that direction, and this is going to be going down, but eventually the opposite takes place there. So we don't know where this is going to happen, but it's going to come down and eventually go back up. And hopefully you can come back to this, and we'll throw some symbols in. I'm going to have a little fun with this one right now, just to give you a heads up on cubics. All right, so let's actually give some names here to numbers and give you a chance to see how to construct graphs. So let's call this, how about we call this 3, 10. 3, 10, and let's go down. Let's go down at a 4-to-1 rate. Let's say we're going down at a 4-to-1 rate there. All right, and then let's get some random value over here. Let's make this 8, 3, 8, somewhere over here, 8, 50. I got different colors going here. Don't know why. 8, 50. All right, so what would that graph have been? Graphing form for a cubic, x minus h cubed plus m x minus h plus k. I'll give you that much. If you really want to dive into this and try your hardest to see if you can get this equation, be my guest. Once you learn how, it's about 5 seconds. I'm sorry to say that, but it is. All right, so you give it as much thought as you want. I'm just going to write it down and talk a little bit about what's going on and why. All right, so for HK, very similar to the vertex of a quadratic, right? Except that this is the point of inflection of a cubic. So we're going to write x minus 3 cubed, and over here we got x minus 3, and that's the linear component. So that's the blue, that's the red, and maybe I should put it in color code. So you got a red graph, you got a blue, and you got K. K is 10, so we'll write plus 10 in blue and red, right? Because they share that. They share that value. So the only question is getting the A and the M term, and I gave you the M, minus 4. Okay, so that's the graphing form for a cubic, because that's what we created. We created a cubic graph out of a what? A linear and a cubic. Okay, now I'm not quite sure if I should have put it here and then just raised it to, I'm a little unclear as to whether or not that's going to resonate with you completely as to why that's the point of inflection, but this highlights the point of inflection. All right, and since I didn't have a constant raising these, I probably should have put it through the origin and then raised it. But let's just stick with what we got, because I already done a bunch of other things here and I don't want to do this again. All right, so now the only thing we're missing is the A term. It's the only thing we're missing. But one thing I can tell you, from 3 to 8 is 5 units of change. And if I change by 5, that's 125 when I cube it. I know for sure I want to get rid of that. Because, I want to put the number 8 in. And if I put 8 in right now, 8 minus 3 is also 5, right? Yeah. And 5 times minus 4 is minus 20. I don't want that either. I don't want minus 20. I'll get rid of that. What do I want? I want to get from 10 to 50. Well, that's 40. So this was 60 over 125, x minus 3 squared, the heck with color code, 4 times x minus 3, plus 10. And if you give me that, I'll give you this. I'll give you that graph. You know, put a 0 in, find the y-intercept, much better graph once you find that. You can find out if, you know, what these values are, these values quickly without calculus. That x value is h plus or minus the square root of minus m over 3a. Okay? You can get that without calculus. M is -4. So you can find out if you have imaginary maxes, not imaginary maxes and mins, but you know, the actual local max and local min values without calculus. All right. So here's our chance now to do a composite where you can put your nascent graphing skills on display. Here we go. Good luck. Our old department head, Mr. Peller, used to give people $1 for this problem. I think if they could do it. Practice like we just did, so I'm hoping that some of you can do that now. All right, so we're going to graph y equals e to the 1 over x without a calculator. We're going to see what that graph looks like, okay? And I'm going to give you the two graphs you're working with, e to the x and 1 over x. I'm going to give you that. You pause the video and you see if you can get a sense of what this graph looks like, which is kind of what we were practicing along the way for this moment. See if we could activate a little bit different part of the brain. Okay. So you pause the video, I'm going to keep talking. All right, so e to the 1 over x means that we're going to put the red graph into the blue graph. So I'll change that to e to blue. We're going to put red into blue. Well, what do I notice about blue right off the bat? It's always positive. So I don't care what I throw in here. It's going to become my input. All of these y values here, all these y values become my input to the e graph. So the question is, what kind of y value are you looking at over here? What are those y values? Well, if you said they're close to 0, you're right. You're absolutely right. They are. They're close to 0 for the longest time. So what's this graph going to look like? Well, you got to know. You have to have a feeling for e to the 0. And if you said 1, you'd be right. So it's got asymptotic behavior for quite a while. And then my y values start to do what? Become more and more negative. More and more negative. So then you're talking about numbers like e to the -30. Do you have a feel for that number? We started this video, it's all about a feel for the discipline. Do you have a feel for that number? Well, this stage of the semester or trimester, we should know that that's reciprocating e to the 30th. E to the 30th, woo! Awfully big number. Awfully big number. So what's this going to become if you put an awfully big number? I'll just throw 9s in there. It's going to 0. So this thing is going to 0. Now the question is, what happens when we're at 0? When you're at 0, it's undefined. You can't get this thing. You can't use 0. You can't use 0. We got a little point that, I guess we'll call it a point of discontinuity. But then again, we're jumping to a different place on the graph. So a point of discontinuity that jumps. Yeah, you'll have to ask a math major how to describe that. This guy's above my pay scale. All right, next problem. What happens when we just get past 0? Oh, my y values here. What are those y values? They're huge. So those y values that are huge become my huge x values, my huge input into this graph. And what happens when I put huge inputs into e to the x? Huge input. I get a huge answer out. Woof. Okay, so I see some asymptotic behavior here. Huh? Huge. And then what happens? My y values head back to what? Head back to 0. And what did we say e to the 0 was? 1. So we get asymptotic behavior over here. That's what the graph looks like. Okay, and hopefully, maybe somebody got it. We'll see. Now let's go back and talk about what you were looking at and why. All right. So we're back to the first graph. Okay, yeah, the old guy's got. All right, let's go watch. All right, so we multiply. Maybe I need a little eraser here to get back to where we were. So this was multiplication. And so what might we have been looking at? What might we have been looking at? Now, a red graph could have been, I don't know, how about 2x? Let's see, where am I at here? Red color code. Okay, so maybe this is going up at x minus 2 is a factor. All right, and maybe this one's going down at a little quicker rate. So how about minus 2x plus 6? Okay, and if you multiply those out, you get minus 2x squared, 6 plus 4 plus 10x. Let's make that, can I make these numbers slightly? No, that's all right. 2x, what did we say before? 2x plus 2 maybe, x minus, let's make this 6. X minus 6, all right. So that's going to be 12, 14. Yeah, let's do that. So 14x, no, that's not what I want. Let's make this x minus 4. So that's going to be, I just want to do a quick minus b over 2a that's not fractional. So minus 8, doesn't matter. I'm not getting there. So plus 8x and 2 is 10x. So I got right back where I was before. That's okay. We'll deal with it. Minus 8. There we go. All right. So what would we have had? We would have had an intercept at minus 8. There we go. We've got minus b over 2a, minus 10 over 4. Now, so at 2.5, I'm getting my max. I'd have to drop that number in to find the y value that goes with it. We've got roots at positive 1. There's positive 1 and 4. Just general speaking, I know it doesn't look that great to scale, but I hope you see that we got a quadratic, right, when we put in some symbols. Over here, what do we call our red graph? We said, okay, that may be going up at 2 to 1. So let's say that that's 2x plus 2, 2x plus 2, and then the blue is going up at 5 to 1. Let's have that be 5x minus 5. 5x minus 5, that puts that at a root of 1. So we got a root there at 1. Oh, we were dividing, excuse me. So we got 5x minus 5 over 2x, what did I say? 2x plus 2, something like that. Plus 4, 2x plus 4, something like that. Now, the reason I just wanted to do that was to highlight what we said over here. Y equals 5 over 2, the proportionality that we had. And I hope you can see that they're to the same exponent. And so there's your proportionality. Because when you go to infinity, numbers like this don't matter. You know, when you go to infinity, those little numbers don't matter. So that kind of gives us a feeling for the end behavior of that graph. And of course, we got roots and undefined moments. When did we have an undefined moment? 2x plus 2 is the red graph. And I obviously practiced at changing the colors here. I should take more time with that. 5x plus 10, 5x minus 10. I don't even know if I said that, but that would have given us the asymptotic behavior here at negative 2, right? Positive 2, excuse me. Positive 2, what makes that undefined? All right. So, you know, when you put symbols with these graphs, yeah, I think you're getting a better feel for it, obviously. So what do we have here? We got x squared. We had x squared, some kind of squared. We were adding what? A linear function. It looks like it's going down at 2 to 1, something like that. 2 to 1, and we started off maybe with an altitude of 4, something like that. Okay, so what can we see? Well, if we're really looking, minus 2x plus 4 is actually that little snippet. Right? So polynomials, you can always talk about the rate of change at the y-intercept. We'll look at that from a non-calculus perspective as well. We just did in this context. So that's embedded there. And then what do you got? An x squared graph taking over. Okay. And what would the x value be? Minus b over 2a. So at x equals 1, At x equals 1, we can now find the height, which is -1 plus 4, I believe, 3. So -1 gets us 3 if I did the math quickly there. And that's attaching some symbols, some actual polynomial equations. We already did the cubic, so I think we're done. I don't know, I think it's a useful exercise to be able to activate the brain in that way, because it gives you a better sense of adding and subtracting the terms and beginning that very important skill of interpreting rates of change. That's all about calculus, rates of change and amounts. And that's what you study in calculus. Next year in trig, you're going to study angles and ratios and angles. Calculus, rates to amounts, amounts to rates. It's a good time to start thinking in those terms. So when you're looking at how graphs change, think about their component parts and how each contributes to that change. And I think you'll mature mathematically a little bit more than if you hadn't considered those issues. All right, so I'm going to close this out, upload it, and use it as an assignment for you to peruse.